All right, good morning, everyone. My name is Janie Montblanc, and on behalf of the Great Basin Fire Science Exchange, LANDFIRE, and our regional landscape conservation cooperative partners, I would like to welcome you to this webinar titled Biophysical Settings Review in the Great Basin, What It Is, How It Works, and Why It Matters, presented by Kori Blankenship with the Nature Conservancy. Before I introduce our speaker, I will go over some webinar details. If you have questions for the speaker or me, please type them into the questions box of your control panel located at the top right of your screen at any time during the webinar. There will be two opportunities for Kori to answer your questions during this webinar, one halfway through and again at the end of the presentation. I also want to let you know that whatever you do in your control panel does not affect the webinar presentation, so you're welcome to type a test message or test your audio at any time during the webinar. If you're having problems with your audio, please open your audio box and check your audio selections. Now I would like to introduce our presenter. Kori Blankenship is a fire ecologist with the Nature Conservancy in Bend, Oregon. Kori's career in natural resources started as a forestry aide on the Wenatchee National Forest in 1995. In subsequent seasons, she worked across the western U.S. as a wildland firefighter for the U.S. Forest Service and National Park Service. She joined the LANDFIRE National Program in 2004 as a GIS specialist at the Missoula Fire Sciences Lab, then moved to the Nature Conservancy's LANDFIRE team in 2005. In her decade plus at the Conservancy, she has facilitated the creation of thousands of vegetation dynamic models for ecosystems across the U.S. and is one of the leaders of the ongoing Biophysical Settings Review and Update project. Welcome, Kori, and thank you for presenting today.
Great.
All right, now
so I think pass me the ball. Is that how it goes?
Yep. I'm going to make you the presenter.
Okay.
Looks great.
All right. Good morning, everyone, and thanks for taking the time to be here. It's my pleasure to be here this morning or afternoon, depending on your time zone, to talk about LANDFIRE's Biophysical Settings Review in the Great Basin. You'll notice on my slide that I've modified it just slightly and put a plus after the Great Basin, and that's because in addition to the Great Basin area, I'll be talking about a west-wide review of sagebrush systems. Before we get started, I want to take a moment to introduce you to the LANDFIRE team. On the top of this slide, you see our mapping team. And the mappers are based primarily at the USGS Aeros Data Center in Sioux Falls, as well as the Missoula Fire Sciences Lab. And then at the bottom, you see the Nature Conservancy's LANDFIRE, which I'm a member of. And we're responsible primarily for education and outreach about LANDFIRE products, and we support the development of the ecological models we'll be talking about today. Here's an overview of what I'd like to cover. I want to start with an introduction to the biophysical settings models. A lot of people are really familiar with LANDFIRE spatial products, but I find that not as many people are familiar with state and transition models. So we'll just go over some basics there so everybody's on the same page. Then I want to look at how the biophysical settings models are used, including a real-world example from the Great Basin. And then I'll wrap up with talking about how you can help improve the biophysical settings models through the BPS review that's taking place right now. I like to just cut to the chase when I do a webinar and tell you what I really hope you'll take away from our time today. And it's really two things. One, I hope you'll see that the models are a valuable tool for understanding the basic ecology of ecosystems all across the United States. And the models provide a framework for exploring management actions and testing various management scenarios. And the second take-home message I have is that we need help improving these data. The models are based on the collective knowledge of hundreds of individuals, and we need folks to, again, contribute to help update and improve them. Also, kind of some preliminary just words before we get into the meat of the discussion here. I like to talk about how any particular region or locale fits into the bigger scheme of things, because LANDFIRE is a national project, and our sweet spot is providing data for large-scale applications. Specifically with the biophysical settings models, our models have less detail generally and cover broader areas than some local models that you might use. For example, the Integrated Landscape Assessment Project, or ILAP, produced similar models to LANDFIRE's for Oregon, Washington, Arizona, and New Mexico. But those are really meant to be applied at a finer scale than the LANDFIRE models. Also, in contrast, LANDFIRE provides reference conditions, and not all other modeling projects do that. In particular, ILAP did not provide reference conditions. LANDFIRE models cover all lands, forest and rangelands, and we have that important link to the spatial data. So that's really our niche, but we recognize that in different areas, people have locally preferred data sets. And so the idea here today is that hopefully you'll learn something about how LANDFIRE data can be applied and how they can fit in with more local data sets that will have greater relevance at finer scales. Okay, so now into what I told you I was going to talk about, the first item being an introduction to the biophysical settings models themselves. And I like to just walk through an example to illustrate how they work. So the example that I'm going to walk through today is for the Intermountain Basin's big sagebrush shrubland. All LANDFIRE models have two parts. There's a description and a quantitative state and transition model. And together, those two things describe the basic ecology of a biophysical setting prior to Euro-American settlement. And I'll step back here just a minute because I realize that I haven't described what a biophysical setting is. So a LANDFIRE biophysical setting represents a vegetation concept that could be supported at a given site given that its biophysical environment. That's the soils and the climate. And it also includes the natural disturbance regime. So it's not just climax veg, it's the vegetation that the site could support given the natural disturbance regime. Okay, so first I'd like to walk you through the part one of a LANDFIRE biophysical settings model, which is the description document. And this is really nice because we're not just handing you a model with a bunch of different numbers. This description document really helps you interpret those numbers and gives a lot of good just baseline information about these ecosystems. So one thing that I like to do right off the bat is I look at who contributed to the model, and you see that here in this general information. There's a list of contributors, and ideally there's also a list of reviewers. In this particular system, those fields are blank, which means it didn't receive review the first time around. And then as you go down through the description, you'll see a list of dominant species, a description of the geographical range as well as the biophysical site, more information on the vegetation community. You'll get a description of the disturbance regime. You'll get some information about what systems may be adjacent to this system or how it might be difficult to identify, or some keys to identifying it on the ground or via satellite imagery. And then there's a whole section on vegetation classes, and these are the states from the state and transition model. So hopefully you'll understand these better when we take a look at the state and transition model, but what I want to highlight here is that each state in the model is described. So for example, this particular model starts with an early development class, and you can see there's some structure information, both height and cover, about that class, as well as indicator species and a brief description. And as you scroll down, there's each class, each state in the model is described. And then after that, you'll find the disturbance description. There's a table with fire information. For this particular ecosystem, it's modeled with an all-fire return interval of about 115 years. And then finally, there's a list of references at the end. So that's the description document. And that is paired with the state and transition model. Originally, LANDFIRE developed its state and transition models in a software called the Vegetation Dynamics Development Tool, or VDDT. That model has since been superseded by another model called STSIM. It has all the same capabilities of VDDT as well as a lot of additional functionality, which is why we've moved to it. And, but you can still get the models in VDDT. So we build the models now in STSIM, and you can see this particular model or ecosystem is described by 5 states. You've got an early, a mid-open, a mid-closed, a late open, and a late closed. And the numbers on each box are the age range for that state. So on average, your early state is going to last from 0 to 19 years. Your mid-open from 20 to 59, etc. And then I labeled these with some information from that description document to help you understand them. So the early stage is really grass-dominated. Then there's an open shrub stage, which develops into closed shrub over time. And then the late phases have various amounts of pinyon juniper encroachment. Now, our state and transition models, LANDFIRE state and transition models, are similar in concept to ecological site descriptions, which some folks may be familiar with, but our models again describe a reference condition. Ecological site descriptions will typically have a single state to represent the reference condition. So all of these 5 boxes here would be in one box in an ecological site description model. And then they'll include various degraded or departed states. And so their model is a little bit more management focused than ours. But a lot of the same concepts apply. So if you're familiar with ESDs, it's quite easy to then understand LANDFIRE's biophysical settings models. So now, walking through this model, the arrows here represent the dominant succession pathway. So as the vegetation ages, it will go through these various states. And then there are various disturbance probabilities. These blue arrows show the fire probabilities. Well, it shows the fire transition, excuse me, but there is actually a probability associated with each transition in the model that shows how often this transition is likely to occur. This big sage system also has insects and disease probabilities associated with it. These are basically opening up closed states or taking PJ states back to a shrub state. And there are also drought transitions here. For example, the late one closed drought, a drought there could be severe enough to take you back to that early grass-dominated phase. And again, there's a probability associated with each of these transitions in the model. Now, what we do then, after we've built this model with all of the states and the transitions and the probabilities, is we run it out over time. We run it for 1,000 years, and we average the conditions over the last 500 years of this simulation, and that becomes our reference condition. So one of the things that we average is the state class proportion over time. So in this particular system, what you see is that about half of the landscape on average is going to end up in this mid-1 open, or your open shrub class. 25% on average will be in your closed shrub class. And then you'll get a little less, well, around 5% in each of your PJ encroached states, and maybe 15% in your early grass state. you can then compare these reference conditions to the current condition or the current amount of the landscape in each of these states. We also pull out of the model the average fire frequency over time. And what these graphs show is the last 500 to 1,000 years of the simulation. And I don't necessarily expect you to read the graph, but what I wanted you to see is that there's some variability over time because the model is stochastic. And then, we end up with the overall fire return interval of 115 years. But we also get an estimate of the surface, mixed, and replacement severity fire return intervals. Okay, so this is my place that I've noted just to take a little break and see if there are any questions. That's my overview of LANDFIRE state and transition models, and I thought this would be a good place just to check and see if anybody has any questions about that information. As Jenny said, you can type into your chat panel.
Yes, please type into your, it's titled questions, so type in your questions box. Yeah, we have a question so far. Chris Bowman-Prideaux asks, 1,000-year time steps in model, but how many times did you run the model?
Yeah, good question. The LANDFIRE standard is to run 10 Monte Carlo simulations for 1,000 years over 1,000 simulation cells.
Great, thank you. If you have any follow-up, Chris, feel free to type it in. So far, we don't have any other questions.
Okay. And we'll also have a point at the end, obviously, for questions. So we'll just keep moving along here.
Okay. Oh, wait, I do have another one.
Great.
Dave Tart asks, with a mean fire interval of 115 years, how do you get stands 999 years old? What % of the areas, that's all I have.
Dave, so mean fire, how do you get stands that are 99 years old? Well, what happens, it's a probability for any given pixel. So there are some pixels that will experience fire and some that won't. So I think maybe the question is how, if the fire return interval is 115 years, how would you maybe get to these later states?
Yeah.
I guess I'm not quite sure. Okay.
I said, how do you get to stands 999 years old?
Oh, well, the 999 is just sort of a placeholder that says this state will, or this class will persist unless it has one of the disturbances in the model. So anyway, there is a probability in any of these earlier states that you'll be eligible for a fire transition, but not all cells will experience that, and that is how you'll get to the late states. But notice that the late states in the results were about 5% of the landscape. And so not very many cells will age into the late class because most of them are going to have a fire before that. Hopefully I've answered that question.
He says, so this model is spatial, pixel-based?
Great question. No. We run it aspatially. STSIM actually has spatial capabilities now, but we don't use them. A simulation, a pixel is basically a way of saying a simulation cell or a unit, but it's not located on the ground. It's just a simulation unit.
Okay, and Chris was following up and saying you can't model over 1,000 time steps, so that's why you'd have 999. Is that correct?
Yeah, that's right. And again, it doesn't really matter in this case because if a model, if a simulation cell in late one closed gets to 999 years old without being affected by a disturbance that takes it elsewhere, it's just going to continue here. It doesn't go anywhere.
Okay. And Eric Nielsen asks, are models spatially explicit, i.e. Consider the arrangement regarding fire spread, etc.?
No, and that's an important point. They're not spatially explicit, although as I said, in STSIM there is a spatial capability built into it, so you could do that. And it does not, when the model simulates fire, it looks at an individual pixel and the probability built into the model for fire. It does not simulate anything based on adjacency or what cell is next to it or uphill or downhill. It doesn't know any of that. It's just looking at the probability for fire at a given point on the landscape.
Okay, great, thank you. That's all the questions.
Okay, great questions, thank you. All right, so I want to talk a little bit about how the models were created. It was through a collaborative process facilitated by the Nature Conservancy's LANDFIRE team. And we went around the country holding workshops. We worked with people via webinar and individual meetings. In all, we had over 700 people who contributed to the set of models we have now. And so, again, it's just this, it takes a lot of people and a lot of different expertise to build this kind of information. As with all data sets, these LANDFIRE biophysical settings models have certain strengths and limitations. One of our strengths is that we just cover so many ecosystems. Every single ecosystem that LANDFIRE maps, we have a model for. And in some cases, we have multiple models. So for example, your widespread mountain big sagebrush systems, which occur all across the West, will have several different models to represent them. Another strength of our model set is that it doesn't stand alone. It's connected to spatial data. Every biophysical setting is mapped on the ground. We also map the current location and distribution of each state in the model. And that can be used to look at things like vegetation departure. Another strength is that, and hopefully you can imagine my air quotes here, these models are relatively easy to use. It doesn't take, a PhD in programming experience to run them. But even if you don't believe me that they're easy to use, I can tell you that at least they're supported by the LANDFIRE program. We have a number of tutorials and guides that help people use the models and the spatial data. And you can always call us. All of our information is on the website, and you can email or call, and we will, to the best of our ability, help you with your data questions. Also, I feel like there's really good documentation with our model set. We went through that description document, so again, we're not just providing a bunch of numbers in that model environment. We've got information written in English that just about anybody can understand that accompanies the model. It also states important assumptions about how the model was built. And again, I just want to emphasize that our real sweet spot with the LANDFIRE data is the large landscape level. Some limitations are that the LANDFIRE models are built as reference condition models. They do not include, when you get them just out of the box, any information on management or climate change. But you could add that information in yourself. So they can hold that information, you just have to add it. We also had a number of modeling constraints when we built the model. Most of the constraints were aimed at maintaining national consistency. Because we are a national program, we needed to have some rules in place so that models would be comparable across the country. There's a real wide range in the amount of data available to support the development of these models. One of the constraints we had was that we didn't allow people to model more than 5 states for a biophysical setting. The models are non-spatial, and that's both a strength and a limitation. I put it as a limitation. Obviously for some spatial applications you would need that, and you could now in STSim simulate the models spatially. You'd have to bring in some additional data to do that. But being non-spatial isn't always a limitation. It sometimes is a strength. It takes less computing capability, less data, and less technical expertise to run them aspatially. So that's kind of a strength and a limitation, I guess. It depends on your objective. Another limitation with all models in this type are that they can be difficult to validate. There's just limited information out there, limited historical data with which to build the models. So there is, some expert judgment involved here. On the flip side, we've tried to be very clear about the assumptions that are being made. So you can evaluate that information and change it if you feel like you need to for your particular application. And that gets to my last point, which is LANDFIRE models will provide a great starting point, and you can review them and revise them as needed for local application. Okay, this is a really busy slide, and I don't expect you to understand the whole thing, but what I'm hoping to convey here is that the LANDFIRE biophysical settings models are related to various spatial products. And so by improving the biophysical settings models, we're also going to be able to improve several of the spatial data layers. So for example, succession class structural information is applied to biophysical settings and some other existing veg information to map succession classes. The reference percent is applied to a biophysical setting compared to the current S-class distribution and used to calculate vegetation departure and vegetation condition class. And then the fire frequency and severity information is taken from the model description, applied to a biophysical setting as a lookup table, and used to map the fire regime group suite of data layers, which includes the mean fire return interval and the various fire severity layers and fire regime group. So the quality of the biophysical settings model has a direct impact on these other LANDFIRE spatial data products. Okay, now let's talk about model use. This is a great graphic that I borrowed from Hugh Safford and others, and it illustrates conceptually the value of this historic information. And so here you see they give a range of variation on the y-axis and various management strategies along the x-axis. And so for the first example, you see a condition where the historic range of variability overlaps largely with the current range of variability for an ecosystem and the future. And so that's a situation where you might want to look at strategies that maintain the current state. In a situation where you have a historical range of variability that looks to be like what you expect for the future range of variability, but the current range of variability is different, you might be in a restoration type scenario. If the historic range of variability and the current range of variability are similar but different from what you would expect in the future, you might look at adaptation strategies. And then you can see the others here. There's a maintain rather than restore, and then there are also some restore then adapt type situations where the current is different than the historic, but that's also different than the future. So the historical information here is providing the context for evaluating where you're at today and where you might want to go in the future. I also want to note here that the historic condition is not necessarily the desired future condition. That's going to depend, landscape by landscape. Okay, so that's conceptual use of LANDFIRE's biophysical settings models. On the web, through the LANDFIRE's web-hosted application map, or WAM, you can find a lot of real-world applications. So I took a snapshot of the Great Basin area off of this web map. Each of the orange dots here can be clicked on and it'll pop up a short paragraph description of a real-world application and then link to additional information. The map just has selected uses of LANDFIRE data. This is certainly not all. It's just a sample that we found interesting that we've collected. So you can read about all kinds of different things that people do. When you click around the Great Basin, you'll find a lot of work by Dr. Louis Provencher of the Nature Conservancy, and he uses models like LANDFIRE models. He generally started with LANDFIRE models, but he's done a lot of additional work to add in additional information and refine them locally. And he uses them to look at costs and benefits of restoration work at various landscapes around the Great Basin. So there's a lot of information there. But I just pulled out one particular study that I thought would be of interest to this group that illustrates how LANDFIRE information and state and transition models can be used to support management activities. So this is the case study I chose. It's about the economics of fuel management. And in this study, Taylor and others used a state and transition model to simulate wildfire suppression costs with and without fuel treatment. They were trying to answer the question basically, is fuel treatment economically efficient? So I'm just going to walk through a really high-level overview to show how LANDFIRE data and state and transition models help answer this type of question. This is a graphic illustration of the state and transition models they came up with. They looked at Wyoming sagebrush and mountain big sage, but I'm just going to show the data for mountain big sage because we've already been looking at mountain big sage, so we'll just continue with that. So their state and transition model starts with a healthy sagebrush state where there's sagebrush and perennial grasses and minimal invasives. And that state, as you can see by these red arrows, is maintained by wildfire, and then the green arrow, it's also maintained by successful fuel treatments. Now, over time, in the absence of fire or fuel treatments, the model will transition to the pinyon, juniper, and mature shrub stage shown here. This state can be successfully treated, and you can return back to the healthy sagebrush state either through treatment or through wildfire. But without fuel treatment or wildfire, the PJ shrub stage will transition to this closed canopy pinyon juniper state. And the closed canopy pinyon juniper can be restored back to healthy sage, but it's increasingly costly to do that. So you'll see that there's the green arrow representing a successful treatment and restoration back to healthy sage, but there's also a yellow arrow representing the possibility that treatments will fail. And if that happens, you'll transition to the annual grass-dominated phase. And in the annual grass-dominated phase, the wildfires are larger and they're more frequent. Treatment becomes increasingly costly in this state, and the success rates are low. So you see, sorry, it's a little hard to find my mouse here. Maybe I'll just go without it. There's a yellow arrow that cycles back to annual grass, so treatments are often unsuccessful, but there is also a probability of successful treatment represented by the green arrow. Also, if you have wildfire, as represented by the red arrow, you will just maintain in that annual grass state. So to build this model, Taylor and others took the wildfire return interval and transitions rate between states from LANDFIRE rapid assessment models. And they had to use other data for the closed canyon, pinyon, juniper, and annual grass dominated states. Those are not reference states, so there was no data in the LANDFIRE model to build those states from. Okay, then in addition to the information about the states and the transitions, they added in the treatment costs. So you can see the cost here associated with each of the various treatments. And notice that the treatments get more expensive as you get into your degraded states, your closed canyon, pinyon, juniper with annual grass, and then your invasive annual grass dominated state. They also needed to add in the cost of wildfire suppression. Here I've highlighted the mountain big sage part of the table. And you can see that the lowest cost per acre for fire suppression is in the healthy sagebrush state. And the highest cost per acre is in the closed canopy PJ state. And here are their results. So I want to just draw your attention to a few things on this busy table. Here you can see that they have higher success rates in the healthy state, as well as lower treatment costs, significantly lower treatment costs, especially if you look at the cost, over $2,000 per acre on the invasive annual grass dominated state. And they have lower suppression costs in those healthy states. So the conclusion really to this study is that in terms of the suppression cost averted, fuel treatment is really only economically efficient in the healthiest ecological states. It's not cost effective to treat the degraded and invaded states. And that's again because the transition to the degraded states leads to increased fire frequency and increased suppression costs. Now, the authors do note, and this is an important caveat, that their model is only measuring economic efficiency in terms of wildfire suppression cost savings. If they were able to quantify ecosystem goods and services, they might get a different result here. So in summary, Taylor and others built on a reference condition model provided by LANDFIRE. They added in a lot of information on management activities and costs, as well as fire suppression costs. And with that, they were able to analyze the costs and benefits of fuel treatment. Okay, so now that we've taken a look at what a LANDFIRE biophysical setting model is and how those models can be used, both conceptually as well as a real-world example, I want to talk about the review effort and how that works. The LANDFIRE models are almost a decade old at this point, so they've had no review or improvement in almost 10 years. And this review offers us a chance to improve and update the models. We know that there's new science available to improve some of the information in the models. And we know that there are just some errors that we made along the way, as well as some inconsistencies in the model set. And we want to catch those and correct them through this effort. So we are asking for individuals to help us with that review. We built the models through a collaborative effort where people volunteered to help us, and we're using that same model during the review. This is not on anyone's objectives, but my own. So we're asking for volunteers, people that have expertise in vegetation and fire ecology and forestry and range specialists, etc., to help us review this information. And the way the review process works is we've built a website shown here, landfirereview.org, and we ask that people go to that website, spend 10 or 20 minutes learning about the review process. Then you can download a biophysical setting description for an ecosystem of interest. The length of those description documents varies, but most are about 4 to 10 pages long, and it'll come as a Word document, and we've inserted into that Word document all the quantitative information from the state and transition model. So you don't have to model, and you don't have to have any special software. If you can open a Word document, all the information will be there. What we ask is that people open that Word document, they turn on track changes, they read through it, and provide feedback. You can submit your review via email, and then we'll take that review along with reviews we get from other people and update the models. And hopefully, you know, if you do participate, you can feel good about improving these products that support land management. We also have a special review effort going on for a few very widespread ecosystems, and in the West, we're looking at the Intermountain Basin's big sage shrubland and the Intermountain Basin's big sagebrush steppe. We're calling these macro reviews because what they're designed to do is to encourage people to look broadly across an entire ecosystem. And so the big sage systems are really great for that because they are so widespread. The map I've shown here is for the Intermountain Basin's big sagebrush shrubland, and regardless of the color on the map, it's all big sagebrush shrubland. What the colors represent is areas where we have a different state and transition model. And we made different state and transition models in these different areas to represent different growth rates and different disturbance frequencies. So we needed a new model to represent the system in these areas. But the question really is, have we adequately captured the ecological variation here across the range of the big sage shrubland? And that's what the essential question we're trying to get at with these macro reviews. And to do that, we've provided various pieces of information. Again, this is all on the main website, landfirereview.org. And so one of the things we did is provide this map of fire regimes summarized up to a map zone. And so, for example, this red area in the upper left shows that for the Columbia Plateau and most of eastern Oregon, we've modeled a fire return interval for big sage shrubland at 33 years. But across the Great Basin and beyond, we've mapped or modeled and mapped a fire return interval of about 115 years. And so you can see how it varies across the range of the big sagebrush shrubland. And again, the question is, does this seem right to you? And if not, where did we go wrong? And then we need to go back and correct or adjust the model to more accurately represent what you think is going on the ground. So that the macro review is just a specific type of biophysical setting review. All the information for any type of review, whether it's the macro review or otherwise, is all hosted on the same site, landfirereview.org. And if all else fails, you can always contact us, and we'll help you through the process. I want to offer a few reasons why I think you should participate or consider participating in this review. One is that the review and the biophysical settings models offers an opportunity to multiply your impact. If you know about these ecosystems, you can participate and translate your knowledge into these important products that are used in all sorts of applied and research settings. A second reason to participate is to improve the data that are used to manage land. So if you go to that web-hosted application map I showed, you'll see how the models are used in land management all across the country. A particular land management application that I think is relevant to this group is that the model data will help improve some of the data used in the sage-grouse conservation effort. So if you go to the BLM's Greater Sage-Grouse Effectiveness Monitoring Instructions Memorandum, you'll see LANDFIRE's biophysical setting map identified as the data set for quantifying the historical extent of sagebrush. And that's going to be the baseline from which change is measured over time. And so the biophysical setting description documents are really the thing that the biophysical settings map is built off of. So by improving the biophysical settings descriptions, you improve LANDFIRE's biophysical settings map, and then there's better data to support the sage-grouse conservation monitoring effort. A third reason is just fun. A lot of us spend time doing things more administrative in nature, but this provides an opportunity to kind of get back to basics and think about ecology and disturbance and succession. All right, so I want to wrap up here, back to my take-home messages. I think, and hopefully you've seen today, that the models really are an important piece of information because they help us understand very complex ecological processes and relationships. They also provide a framework for exploring management actions and testing various management scenarios, analyzing the effects of alternative management approaches, and looking for restoration opportunities. All these things are possible in the state and transition modeling framework, and the LANDFIRE models provide an excellent start for you. And we need help improving this information. So if you can help, we estimate that it takes, maybe an hour to 2 hours to review a biophysical settings model, and we would encourage and welcome and be most appreciative if you could help us review the models. I'll end here with some online connections. At the top, again, is the landfirereview.org site for all the information about the biophysical settings review. The LANDFIRE program page, landfire.gov, that website is an excellent resource for accessing all the spatial, well, really all LANDFIRE products. That is the point to get LANDFIRE products. The Nature Conservancy's Conservation Gateway is a companion site which focuses really on the applications of LANDFIRE data as well as support materials. You can follow us on Twitter. We have informational videos and tutorials on YouTube. If you want to get information about the program, we do periodically send out bulletins and postcards, but you have to opt in, and there's a URL here for that. But probably most importantly, because I don't expect you to get all of these URLs, is if you could just remember landfire@tnc.org. You can shoot us an email, and we can, opt you into the bulletin or get you other information as needed. And then you can see my contact information there. You're always welcome to contact me. If I can't help you, I will try to get someone who can. So thanks again for tuning in, and I would welcome any questions you have.
Great, thank you so much, Kori. So a couple questions just going back to the first half. What is the accuracy of the state maps?
The succession, yeah, okay, the state class map. The accuracy of that map is not assessed individually, so you can't go to landfire.gov and get an assessment, but what you can do is get an assessment of the pieces that build that map, and that's existing vegetation type, cover, and height. Those things have accuracy assessments for them. The target accuracy for LANDFIRE is 60 to 80%. It varies quite a bit by type, and so you can go online and get those reports. Biophysical settings is also a component of mapping the state classes, but we don't have an accuracy assessment for that because that's a concept. We don't really have good data with which to determine whether we've mapped it right or not.
Okay, thank you. And does a succession class equate to a state, one of the 5 boxes?
Yes. Sorry, it gets really confusing with all this terminology. I tried to be consistent, but yes. A succession class is the same thing as a state class, and it's sometimes even called an S class to make it a little more confusing.
Okay, thanks. All right, can you download the state and transition models if you want to play with them during the review?
Absolutely. We tried to make the review as easy as possible, and we figured that most people would be comfortable with a Word document, but fewer would be comfortable with the state and transition models. But they are all available if you want to look at those. And in fact, let me just see. I'm going to go to the review website now. Oops. There you go. This is the review website, and there's a special tab for review. It talks about individual BPS review and macro reviews. But if you go to the individual BPS review tab, there's a simple set of instructions for reviewing, and you'll see here under number 3, review and edit the simulation model, and we put it as optional because, again, all of that information is in the description document. But if you're familiar with state and transition models, you may be most comfortable with looking at it in the modeling software. So there are instructions for doing that here. We also provide some really good information on an overview of the LANDFIRE models and how to alter and run a model in STSIM. And then also on this right side, notice all the tutorials we have that deal with using the state and transition models, how to edit them, how to graph them, how to run them, all that kind of stuff. So we tried to support that users as much as possible. But if you don't find what you need here, just contact me.
Great, thank you. On the first macro review slide, zone 18, there seems to be very little sagebrush blue. Is that the only place you have sagebrush?
Let me just see. Okay, so looking at zone 18 right here, it looks like, it's sort of scattered here in southeastern Idaho. That's the only place where Intermountain Basin's big sagebrush shrubland was mapped. There may also be the big sage steppe here, and there are a handful of other sagebrush systems that LANDFIRE maps. But for the macro review, we're only looking at the 2 big sage systems. So this is where we mapped it, and we would welcome any comments about whether we've undermapped it or overmapped it in specific geographies. That's one of the reasons why we provide these maps, is so that people can say, hey, wait a minute, that doesn't look right. So we would welcome feedback on that.
Great, thank you. All right, well, that looks like the last question. If anyone has any further questions, you're welcome to begin typing them in. Oh, and I wanted to unmute Jeannie Patton in case, I didn't know, Jeannie, if you had any comments.
I have nothing to add to what Kori just did. LANDFIRE@tnc.org is the email address in case anyone else wants to get straight to LANDFIRE, and Blankenship@tnc.org is Kori's direct mail. So I think we've covered it.
Great. All right. Well, thank you. Thank you, everyone, for your participation. Oh, we do have another question. When do you want the review completed by? That's an important question.
Yes, great question. Thank you for the reminder. Our official deadline is October 31. However, it's very possible that we can accept reviews up until the end of the calendar year. But if you want to go past the October 31 deadline, just let us know, and we'll work with people on an individual basis. That allows us to say, hey, I'm not going to gather all the reviews on this particular ecosystem because I know this person's going to provide review in December. I'll wait on that, but I can work on these others. So October 31 officially, let us know if you want to go to the end of the calendar year.
Okay, thanks. Did you get permission to use the Beatles likeness?
Oh, I don't know. Good question. That's not my area.
Well, since this isn't for publication, we just grabbed it.
All right, great. Okay, thanks again, everyone. I will post the recording of this webinar on our Great Basin Fire Science YouTube channel this afternoon, and the link will be automatically sent to you through the GoToWebinar system tomorrow. If you have further questions regarding this or future webinars, please email or call me anytime. Again, thank you for attending, and thank you so much, Kori, for your presentation.
Thank you. Thanks, everyone, for being here and taking the time to listen.
All right, great. Have a great day, everybody.
Bye-bye.
Bye.